Hello everyone. Our project is KADALKAVAL, meaning Sea Guardian in Malayalam. It is a cloud-native sustainable fisheries monitoring system developed for Kerala coastline using Microsoft Azure. The system monitors marine conditions such as sea surface temperature, weather conditions, vessel movement, and fish zone probability using simulated IoT buoy data and Azure cloud services. Our main goal is to improve fisher safety, support sustainable fishing, and provide real-time coastal monitoring through a scalable serverless architecture. Kadalkaval is designed as a smart coastal monitoring platform for Kerala's fisher communities. The system simulates IoT biostations across different coastal regions and generates marine data every 5 minutes, including SST, salinity, chlorophyll concentration, weather condition, and vessel coordinates. The data is processed using Microsoft Azure services such as Event Hubs, Azure Function, Azure SQL Database, and Azure App Services. By combining cloud computing and marine analytics, the system provides real-time alerts, fishing zone prediction, and environmental monitoring. Problem statement. There are four major problems affecting coastal fisheries. Firstly, fisher folks often lack real-time alerts for dangerous sea conditions such as storms and high waves. Secondly, illegal vessel movement into protected marine regions is difficult to monitor continuously. Thirdly, fishers do not have scientific guidance for identifying productive fishing zone, leading to reducing efficiency and increasing fuel consumptions. So finally, climate-related ocean changes such as SST anomalies are not continuously monitored at the coastal level. Kadalkaval addresses these problems through a cloud-native real-time monitoring platform.
So thank you, Vighnesh. So let us talk about the project objectives. Our project focuses on four core objectives. The first objective is real-time SST anomaly detection. The system continuously monitors sea surface temperature and identifies temperature outside Kerala's safe marine range of 27.5 degree to 30.5 degrees Celsius. The second objective is weather alert classification. The platform classifies marine weather condition into storm alerts, cyclones, high wave activity, or clear conditions. The third objective is vessel violation detection. The system monitors vessel movement and detects unauthorized entry into marine protected areas using geospatial calculations. The fourth objective is fish zone prediction. By analyzing SST and chlorophyll concentration together, the system estimates region where fishing productivity is likely to be higher. These objectives collectively improve fisher safety, environmental monitoring, and sustainable fisheries management. So, this slide highlights the sustainable development goals supported by our project. The first SDG is SDG 1, which is no poverty. Since fishing is a primary livelihood for coastal communities, improving fisheries efficiency and reducing unnecessary fuel consumption directly supports fisher income and economic stability. The second SDG is SDG 2, which is zero hunger. Sustainable fisheries contribute to food security by improving marine resource management and reducing overfishing. The third SDG is SDG 13, which is climate action. Our platform continuously monitors sea surface anomalies and marine weather conditions, which helps it to track the climate-related ocean changes and generates early warning. The fourth SDG is SDG 14, which is life below water. Through vessel monitoring and marine protected area violation detection, the system supports marine biodiversity conversion and sustainable ecosystem management. What makes KADALKAVAL unique is it combines cloud computing, marine intelligence, and sustainability along with the environmental protection into one Azure native platform. Now, Arjun will walk you through the technological stack of this project.
Thank you, Deon. Our entire project is built on Microsoft Azure cloud infrastructure. The first component is Azure Event Hubs. Event Hubs act as a real-time streaming ingestion pipeline that receives voice sensor data from all virtual coastal stations. The second component is Azure Functions. We implemented 4 serverless Azure functions for SST anomaly detection, weather monitoring, vessel violation detection, and fish zone prediction. The third component is Azure SQL Database. It acts as a centralized cloud data store for marine telemetries, alerts, vessel detections, and fish zone records. The final component is Azure App Service. Both the React dashboard frontend and Fast API backend APIs are deployed through Azure App Service. One major advantage of this architecture is scalability. Since Azure manages infrastructure automatically, the systems can scale dynamically depending on incoming telemetry volume. System architecture. This slide explains the complete cloud workflow of KADALKAVAL. At the bottom layer, virtual IoT voice stations continuously generate marine telemetry data every 5 minutes. This telemetry is streamed into Azure Event Hubs, which acts as ingestion layer for real-time event processing. Azure functions then consume these incoming events and process them automatically. Each function performs a specialized operation such as SSD anomaly detection, vessel monitoring, weather classification, or fish zone prediction. After processing, all structured data is stored inside Azure SQL database. Finally, the React dashboard accesses this processed information through fast API backend and visualizes it for end users. This creates a complete end-to-end cloud-native event-driven architecture. Now I call upon Adi to discuss on project workflow.
Thank you, Arjun. Now I'm going to start with mine. This is one of the most important parts of our project because it demonstrates serverless cloud computing. The first Azure function is the SST anomaly detector. It triggers whenever buried data arrives through Azure Event Hub. If the SST value exceeds safe thresholds, the function generates alerts. The second function is the weather alert function. It processes marine weather data and classifies conditions into storm alerts, cyclones, heat waves, etc. The third function is the visa violation detector. It processes visa coordinate data and uses harvesting geospatial calculation to identify unauthorized entry into marine protected resource. The fourth function is the fish zone predictor. It periodically analyzes SST and chlorophyll concentration to estimate optimal fishing zones. The novelty here is that all processing is fully serverless and event-driven. Also automatically executes cloud functions only when events occur, reducing infrastructure overhead. This slide demonstrates the user-facing dashboard interface. The dashboard is built using React and Fast API and hosted on Azure App Service. It provides SST trend visualization, weather alert feeds, visa violation monitoring, fish on heat maps. The platform visualizes marine intelligence in real time and is accessible through a public Azure hosted URL. The dashboard can be used by fish folk, coastal authorities, marine researchers, environmental monitoring agencies. This converts raw marine telemetry into understandable or actionable insights. This slide demonstrates how the project was deployed and validated on Microsoft Azure cloud infrastructure. We deployed React frontend using Azure App Service, Fast API backend using Azure App Service, Azure Function for serverless event processing, Azure SQL database for telemetry storage, Azure Event Hub for real-time streaming. We also verified Azure function triggers, event hub namespaces, SQL database tables, live dashboard hosting, cloud resource status using Azure CLI and Azure Portal. This proves that KADALKAVAL is not a theoretical architecture, but a fully deployed cloud native application running on Azure infrastructure.
Thank you, Aditya. Now, advantages, scope, and conclusion. KADALKAVAL offers several important advantages. First, the system is fully serverless and cloud native, which reduces operation overhead and allows automatic scalability. Second, it integrates multiple Azure services into one unified event-driven architecture. Third, it improves fisher safety through early warning alerts and marine monitoring. Fourth, it supports sustainable fisheries management and marine ecosystem protection simultaneously. The novelty of our project lies in combining the cloud-native event streaming, serverless processing, marine intelligence, sustainability monitoring, and fisheries analytics into one integrated Azure ecosystem specifically designed for Kerala coastline. In the future, the platform can be extended using real IoT buoy hardware, machine learning-based fish forecasting, multilingual Malayalam alert systems, expansion to other Indian coastlines. Overall, KADALKAVAL demonstrates how Azure cloud technologies can power scalable, sustainable, and socially impactful coastal intelligence system. Thank you.
We're going to walk through the project demo and also the code explanation. So right now in my Visual Studio Code, you can see here, this is the backend folder that contains that fetches the data and passes it to the front end. So here we have the Azure configurations and the env file that contains the API or the connection between the SQL query to the data to the front end. So from the Azure SQL, the data will be stored in the Azure SQL that will be passed on to the front end. Okay. So these are the backend files, and we have a simulator also and a requirement code. So this is the function app. As mentioned, we are having a 4 functions also. So each function is having its own primary role, and this code makes sure that it happens. So we purely did the code in the Visual Studio Code console itself. The entire uh, cloud functions were run in the console CLI itself. So as now you can see here, you can see all the 4 functions are displayed over here. You can see the event hub showing 7 messages have received and partition count is 4. And at the bottom you can see the our database, that is the Azure SQL query. Then comes the front end part. The front end I have divided into different pages, and we will move on to the live demo soon. Right now, this is the code implementation, and the code is done purely in React, and the backend is done using Fast API. So this is the SQL query that for reference I've added in the along with the system. These are the main files. Moving on to our project. So this is the main UI of the project, and this is the about page of our project. And it supports both dark mode and light mode in every UI. So as mentioned, KADALKAVAL is the Sea Guardian, a cloud-native sustainable fisheries monitoring system designed for Kerala coastline to support fishery safety, marine monitoring, and also fishing safe fishing practices. So as mentioned, Kerala coastline is around 590 kilometers, and these are all the facts and infos that generally a UI should be displaying. And these are the simulated sensor parameters. So what the buoy sensor gives us is the sea surface temperature, SST, salinity, wavelength, chlorophyll, wind speed, and vessel locations. These are the main 4 cloud components that we have used. Azure Event Hubs, Azure SQL Database, Azure Functions, and Azure App Services. These are the main 4 cloud components that Azure cloud components that we have used in our system. And inside the cloud function, Azure, like inside the Azure functions, we have SST anomaly detector, weather alert function, vessel violation detector, and fish zone predator. And we have used SDG 14, life below water, SDG 13, climate action, SDG 2, zero hunger, and SDG 1, no poverty. These are the UN Sustainable Development Goals we have used in this project. This is the main dashboard. So here you have a live map of the locations of the buoy centers. That will give us the data. That raw data will be given by the buoy. That will be passed on to us, and it will be stored in the database. As you can see here, some rough data will be shown for the people to see, and you can see some active alerts over there. We'll move into it. If we select, like if I'm selecting Trivandrum, you can see the statistics of Trivandrum. These are the data we'll be getting from the buoy. That is the SST, salinity, wave wind, chlorophyll, fish probability, and statistics. So based on the SST and also based on the chlorophyll, these values, we have put it in an algorithm to predict better fish zones, SST trends, and to give alerts if there's any intrusion, if there's any issue. So fish zone based on the probability and also the chlorophyll and all these things, we can see here Thrissur coastal line, it keeps on changing. So now we can see the Kasaragod coastal line is having the better top optimal fishing zone. So this provides the fishing zone. The fishers can look into it and it'll help us to help them navigate much more better. So here you can see the SST trends. So the sea surface temperature trends will be shown here. For the last 30-day history in degrees Celsius is being shown here. And on different stations, what the statistics is being also displayed. So based on the wavelength and also wave height and also the what do you say the SST, we will be giving alerts to the system. Like you can say there's an alert at Trivandrum. So system will give us an alert if this area is not safe. Okay. And you can see here the current vessels or the vessel that are actually in the water. And if it crosses or if it's having a higher speed or if it's crossing the specific zone, we'll alert here that it is severity is high. And we will see the dates of when they have crossed a specific area. So that's all of UI actually works. Thank you so much.